The modern battle space has fundamentally changed. We are no longer looking at isolated, single-platform incursions. The new reality of aerial warfare is the autonomous drone swarm. Imagine 50 kamikaze drones flying in a tight, overlapping formation, moving as a single lethal organism. To the naked eye, it is a terrifying spectacle, but to a traditional computer vision system, it is the ultimate nightmare. Why? Because of visual occlusion. Due to the limitations of communication distances, small unmanned aerial vehicles in a swarm distribute themselves in dense, overlapping formations. As these drones maneuver, cross flight paths, and transform their geometry, they physically block each other from the camera's line of sight. This extreme visual density exposes profound architectural limitations in the prevailing convolutional neural network detectors that have dominated the industry for a decade. Today on the SWaP-C report, we are diving deep into the heavyweight title fight of edge AI. We will dissect the reigning champion, YOLO, and expose its fatal mathematical flaw in swarm combat. Then we will introduce the challenger that is rewriting the rules of computer vision, detection transformers, or DETR. By the end of this episode, you will understand exactly why YOLO fails in the swarm and why transformers rule the future of airspace defense. Let's get into it. For over a decade, the You Only Look Once, or YOLO, lineage has dominated the real-time object detection landscape. Its core architecture relies on a dense prediction paradigm. YOLO divides the input image into a grid-based feature map, generating an exhaustive set of candidate bounding boxes known as anchors. During training, YOLO utilizes a one-to-many label assignment strategy, where a single ground truth object is associated with multiple positive anchors across the grid. This means that during inference, the neural network produces a massive proliferation of redundant, overlapping predictions for every single perceived target. To clean up this noisy output, YOLO relies on a greedy post-processing heuristic called non-maximum suppression, or NMS. The mathematics of NMS follow a rigid sequential procedure. First, all predicted bounding boxes are filtered by a minimum confidence threshold. The remaining boxes are sorted by their confidence scores, and the box with the highest score is selected as a keeper. Then, every other bounding box is mathematically compared against this keeper using a metric called intersection over union, or IOU. If the IOU exceeds a predefined threshold, say 0.45, the algorithm assumes it is looking at the same object and mathematically deletes the box as a duplicate. In sparse scenes, this works flawlessly, but in swarm combat, NMS becomes a fatal architectural bottleneck. When a swarm of 30 drones flies in close formation, the targets physically overlap in the camera's two-dimensional projection. Because these drones share an intersection over union that naturally exceeds the NMS threshold, the algorithm triggers a catastrophic failure mode known as the object merging phenomenon. NMS fundamentally fails to distinguish between individual drones, mathematically perceiving two overlapping UAVs as a single object with multiple redundant predictions. By suppressing the supposedly redundant boxes, NMS literally erases valid targets from the situational awareness map. A swarm of 10 tightly packed drones might be falsely reported as just 3, heavily underestimating the threat. Traditional convolutional neural networks lack the global context necessary to understand that two similar local visual features actually represent two distinct physical entities. To solve this catastrophic bottleneck, the aerospace industry is turning to a paradigm shift: detection transformers, or DETR. DETR represents a fundamental departure from the local heuristics of convolutional neural networks by reformulating object detection as a direct set prediction problem. It leverages the exact same attention mechanisms that power large language models like ChatGPT, but applies them to computer vision. The secret to DETR's supremacy lies in the mathematics of global self-attention. In a traditional CNN, a convolutional filter only looks at a small, localized grid of pixels. But in DETR, the self-attention mechanism allows every single pixel, or feature token, to dynamically interact with every other pixel across the entire image. But the true genius of DETR is how it completely eliminates anchor boxes and the dreaded non-maximum suppression. Instead of predicting thousands of redundant boxes, the transformer decoder utilizes a fixed number of learned object queries to predict a distinct set of n objects in parallel. During the training phase, DETR utilizes a bipartite matching loss driven by the Hungarian algorithm. This algorithm operates in big O of n cubed time, finding the absolute optimal one-to-one mapping between the model's n predictions and the m actual ground truth objects in the image. The matching cost minimized by the Hungarian algorithm incorporates both the classification probability and the spatial accuracy of the bounding box. Because this mathematical constraint forces the model to produce unique predictions, if the network attempts to predict two boxes for the exact same drone, the Hungarian matching heavily penalizes it. Consequently, DETR models naturally and perfectly resolve overlapping targets. By assigning distinct queries to distinct physical entities through global context, DETR can accurately count heavily occluded UAVs, even when their two-dimensional bounding box coordinates are nearly identical. The architecture simply understands the scene better. For instance, in specialized variants like GM-DETR designed for infrared small target detection, geometric relation encoders are specifically used to encode explicit position relations at the pixel level. This prevents the characteristics of obscured UAVs from becoming intertwined, ensuring densely distributed, overlapping drones are never mistakenly identified as a single target. However, for defense AI engineers, the theoretical superiority of a neural network architecture is entirely subordinate to its deployability on physical edge hardware. In the real world, swarm countermeasure systems are heavily constrained by a SWaP-C, size, weight, power, and cost. We have to bring this theoretical math down to the brutal reality of embedded compute modules like the NVIDIA Jetson Orin NX and AGX Orin. Deploying quantized YOLO versus DETR on an Ampere-based Jetson GPU reveals a stark set of trade-offs. YOLO architectures, due to their hyper-efficient convolutional blocks and highly optimized inference paths, are engineered for blistering speed. When deployed using TensorRT with FP16 or INT8 quantization, models like YOLO11 effortlessly hit throughputs over 100 frames per second. This extreme speed is absolutely non-negotiable for the terminal guidance of a kinetic interceptor. When deploying a suicide drone to physically ram a target in a high-speed terminal dive, the flight computer operates on a strict 20-millisecond latency budget to maintain a kinematic lock. YOLO provides that deterministic, ultra-low latency. DETR, conversely, is a massive memory hog. The self-attention mechanisms that give transformers their incredible global context scale quadratically with image resolution, requiring significantly more CUDA memory and bandwidth, pushing the Jetson Orin's RAM to its absolute limits. Processing DETR on an edge module often results in lower frame rates and higher latency. However, what it lacks in blistering speed, it makes up for with strategic zero-error overwatch. The unparalleled occlusion mastery of DETR allows it to perfectly unmerge targets that appear as a single blob to CNNs. Ultimately, the engineering pillars of airspace defense converge on a dual-use paradigm for countering UAV swarms. You deploy the reigning champion, YOLO, for the kinetic kill, but you deploy the challenger, the detection transformer, for strategic swarm analysis. The future of counter-swarm defense is networking both architectures into a unified intelligent kill web. Thank you for joining us on this deep dive into aerospace and edge AI. To stay at the bleeding edge of defense technology and neural network architecture, hit that subscribe button, like this video, and ring the bell. This is the SWaP-C Report signing off.